Hello, everyone. Can you hear me? Yes. Okay. So, welcome to week 10. Today, we'll have a look on storage, physical storage. Okay. And we will calculate few costs of storing data and finding data from the storage that we will have. But first of all, acknowledgement of the country. So I would like to acknowledge the traditional owners of Australia and recognize their continuing connection to land, water, and culture. I am currently on the land of the Buramatagal people and pay my respect to their elder, past, present, and emerging. I further acknowledge the traditional owners of the country on which you are on and pay respect to their elder, past, present, and future. So we have this idea of a table, right? That in a table or in a relation, we have these columns and rows. So columns are also known as attributes or fields. And these rows that we have are also known as records or tuples. Today, you will hear from me these two terms, fields and records. Fields are for the attribute or the column, okay? And record means one row. What we are going to learn today, if we have a query like this, like select everything from one table where some condition is there, then first thing we want to figure out is how these tables are stored physically. Okay, so in the actual storage, how they are stored. Once we know that architecture, how they are stored, then we want to figure out the cost. How much cost do we need to evaluate such a query? Okay, and we'll keep our focus only on one table when we are querying, writing a query on one table. Okay, at that time, what will be the cost? So first we need to define what is the cost, what is the meaning of cost, and then we will try to figure that one out. Okay. So this figure should be familiar by now. We are already familiar with this figure. Every week we see this, right? So today we'll only talk about this part, which handles with the file structure. Okay. Okay, so since we are looking into the physical storage today, first and simple overview on hard disk and main memory. I'm guessing all of you are familiar. If not, then that's fine. So in our computer, we have two types of memory. One is known as main memory or primary memory, okay, typically known as RAM. And another one is secondary memory, also known as hard disk. Hard disk is normally very cheap. RAM, very expensive. That's why in our computer, we have less RAM than hard disk, right? So hard disk is on terabyte level where RAM is few gigabyte, right? 4 or 8 gigabyte, maximum 16 gigabyte you might have, but hard disk currently is going into terabyte levels because of the monetary cost. Durability. So whatever we save on hard disk, the assumption is that everything will remain saved there, right? Even if some crash occurs or even if we turn off the computer, but when we come back, we expect that data will be there. But in RAM or in main memory, that is not the case. Once power goes off, we turn off our computer, everything that we have in the primary memory, all of those are cleared, right? So nothing remains there. So that property is known as volatile. So RAM or main memory is volatile, where hard disk is non-volatile. Hard disk is definitely slow. Reading and writing from hard disk is definitely slow compared to random access memory, RAM. So for sequential access means accessing the data one after another. So sequential means first go to the first position, then second position, then third position, like that. It will be million times faster if we allow random access. So random access simply means that we can go to any position that we want. So if we want to go to fifth position, we can directly go there. We don't have to go from first position. Okay, so that is known as random access. So in main memory, that is allowed. So that's why the name is random access memory. So that's why that is much more faster. Everything that we store, we understand that that is being stored in the hard disk, right? So that's why when we come back, and we log in our system, then we see that all the data are there. Since we will be talking about the physical storage and internal architecture, how hard disk looks like. So in a hard disk, so think about all of these are disks, okay? Simply you can imagine something like this. Let's say you have a collection of DVDs. Okay, so collection of DVDs, there is an spindle, okay, or a stick where all of those disks are connected with one another. Okay, so that's what hard disk is. So there is a collection of disks there. So in a disk, there will be a track. So there are many tracks in a disk. Okay, let me point something out so that you can understand what I'm talking about. So I'm talking about this track. So these are known as tracks, concentric circles that we have inside the disk. So all of those are known as track. Inside the track, part of a track is known as a sector. Okay, so when we store the data, we store the data in a sector of a hard disk. So sector is a very small space. Okay, so we can create a block of data which is consist of multiple sectors. So let's say 10 sector makes up in block. So in a block there will be multiple sectors. Okay, so that's what block means. So this is what I was talking about. Block size is set when the disk is initialized. Okay, so when you buy that hard disk, so the manufacturer already said that one, the block size. So it is typically multiple of sectors. It's typically 4 kilobyte or 8 kilobyte. That is the typical size that we have. So since we have this idea now that there will be disk, in a disk there will be multiple tracks. In a track there will be a lot of sector. If we combine a lot of sector, so that creates a block. Right? So when we try to find some data from a hard disk, let's say you are looking for a song in your hard disk and you want to play it, right? So first what we need to do, we need to figure in which disk that data is, in that disk, in which track the data is, right? So from that track, we need to figure out in which block the data resides, right? So all of this time is known as seek time. So when the arm, these arms that we have, it moves to the desired track, okay? So that's what is known as the seek time. So what is it that you are looking for? In which track do you have that data? This assembly, this arm that we have, okay, for each disk there is an arm. So that will go to the correct track. So that time is known as the seek time, right? So this is what we are looking for. Rotational delay, now you understand that since these are disks, all of this spins a lot, right? So we hear a lot of noise as well, especially when our computer becomes old. Right? So that delay is known as rotational delay because of the spin that we have. Okay. And the final thing is transfer time. Once we figure out where the data is, then the next job is to transfer this block of data from hard disk to our main memory to perform anything. Right? So we have this idea that everything that we want to run, that should be in the main memory, okay, for any sort of processing or any sort of execution. So we need to transfer this block of data into the main memory. So that is known as the transfer time. Someone is asking, how come the disk know where do we store? Yep, so that's what the job is for this arm assembly that we have. So these arms will figure out where the data is. So that's where we are, that's what we will be talking about today, right? So how much time do we need to figure out where our desired data is? So when you write a query, select something from the student table, right? So he needs to know where the data is, right? So that simply means that there will be some process, okay? In computer science term, we call them algorithms. So there will be some algorithm to figure out where the data resides. And from there, it will figure that one out. If you are not familiar with these terms, megabyte, kilobyte, so the smallest is bit, 8-bit, makes up a byte. Okay, so when we have 1024 byte, that makes up a 1 kilobyte. 1024 multiplied by 1023 is 1 megabyte. If we multiply 1024 again, that will become a gigabyte. Then that's how it increases. Okay. Yeah, so we have this idea of block now, that several sectors make up a block. Block might still become very small. Okay, so when we combine few blocks together, that thing is known as a page. Okay. So in the all the data that we have in a table that are stored in a page, that's what we normally say. So page simply means it's nothing but a collection of one or more blocks. Okay, so inside first we have sector, several sectors create a block, several block creates a page. Okay, so that's what the hierarchy is. For the simplicity, today we'll assume that a page means a block. That simply means one page contains only one block. So even if I say block sometimes, page sometimes, those two means the same thing today. Okay, so that's what we will assume. The one page contains only one block. Okay, so let's make some assumption regarding the table that we will have so that we can make some calculation as well. So let's say we have a table. This is our table called relation. Here we have a tuple key and some attributes. Okay, so two attributes are only shown here. To distinguish, the tuple key is underlined, that simply means that is a primary key, so that has some property, right? So that should be unique. Attribute is a normal attribute, so this is not a key, so that simply means that it can be repeated. So familiar yourself with this structure. Relation is the name of our table, tuple key means the primary key, and attribute is any attribute which can be non-unique. So let's say we have 2 million records in this table, and each record, that simply means each row, is 200 bytes long, including a primary key. So this primary key that we have is tuple key, which is 4 bytes. This takes up 4 bytes, and attribute takes 4 bytes as well. So each of the attribute takes 4 bytes. Few assumptions we will make that each page is 4K byte, like I have shown you there. That page could be, or block could be 4 kilobyte or 8 kilobyte, right? So we'll assume that this is 4 kilobyte, of which 250 are reserved for header and array of record pointers. So whenever we have a page, so at the top of the page, there are always some information to read the data in that page. Okay, so how the data is stored. So without knowing the architecture, how the data is stored in this page, we'll not be able to read this data correctly, right? So that information is normally stored as a header data in every page. So this is what that overhead is, or the extra space that we'll need. So in each page, 250 bytes will be reserved for this sort of header data, okay, or all of the pointers that might need to read this file correctly. Okay, so knowing all of these, first of all, we want to answer these three questions. How many bytes per record could be there? How many record per page can we store? And how many pages do we need to store this entire table that we have, which contains 2 million records? Few things. When we are calculating how many records per page, we'll assume that no record is ever split across several pages. So record means one row. So one row of data will not split them into 2 pages. Okay. So if there is not enough space in a page to store that row, then we will move that into the next page. Yep, so this is what just pictorial view is. So this is what we have. So first question was how many bytes per record? That is what we want to answer. In the assumption or in the question, this was already given. This one is saying each record is 200 bytes long, right? So main thing is to understand is that how is the distribution look like. So the primary key that takes up 4 bytes. We have one attribute that takes up 4 bytes as well, and we have other attributes there which takes up the rest of the byte. Okay. So the first question is already answered for us. How many bytes per record? Question is saying each record is 200 bytes long. Okay. So just to make you familiar. Second question was how many record per page can we store? So we assume that all page will be of 4 kilobyte size, right? So in each page we have 4 kilobyte size, and each record is 200 byte long, right? So each record is 200 byte long. So how many record can we store in one page? The equation should be very easy, right? This one divided by 200, that should be the equation, but we have 250 byte reserved for header data. So there we cannot store any record. So we have to subtract that one first. So from these 4 kilobyte that we have, 250 bytes are reserved for header data. So how many space do we have left to store the record is 3,846 bytes. Okay, so this should be very easy to understand what I'm saying. So now this many bytes we have to store the actual rows of data. So if we now start storing, so we know that each record takes up 200 bytes, right? So each record takes up 200 bytes. So if we put them in there, so the first record, after putting the first record, 200 bytes is gone. After putting the second record, another 200 bytes is gone. So that's how we can keep inserting as long as we have data. So it should be 19 records per page. So we have 3,846 bytes in every page, and every record is 200 bytes. So if we simply divide them up, so it will be 19 records, 19 point something, right? So 19 point something will be there. That simply means we will be able to store 19 records. Point something means there is some extra space. Like in this case, there will be 46 bytes. But since each record is 200 bytes long, we will not be able to store that one in here, right? So that's why we will always take the floor. So this symbol that we have, you can see this symbol in here, right? So this symbol means take the floor. So floor means if we have, it's the 19.4, we will always take 19. Even if we have 19.9, floor means that we will take 19 from there. Okay, so that is what floor means. So hopefully this thing is making sense, that we will be able to store 19 record per page that we have. The final question was, how many page do we need for this table? So how many record do we have? We have 2 million record. In each page, we can store 19 record, right? So if we simply divide them up, so then we can see that we'll need this many pages, plus we will have 3 remaining records. So to store those 3 remaining records, we need another one, right? So it should be this one plus 1. So these many pages we will need to store the whole table. If we try to calculate the overhead simply means how many storage we need to perform everything perfectly, right? Not the ideal thing. So how many extra space that we are using. So the calculation should be very simple, that we have 2 million record and each record is 200 bytes. So that should be the space that we need, right? So this should be the calculation that we have, but we can see here, no, this is more than that. Why? Because we have to use some space to store the header data, 250 bytes for each page. And also there are some wastage in each page, right? So in each page, we can see there are some wastage. So we have calculated that in each page, we have 46 bytes wastage there. So because of all of those, we can see now that the byte that we need is actually around 8% larger than what is expected from there. Hopefully this equation is making sense. So this is what actually we need. So this is what the expectation was, right? So if we simply calculate this and make it into percentage, this one will come up as 7.79, which is around 3% overhead, right? So now we can see that because of that wastage of space, because of this header data, so that everything works perfectly fine, we have to waste some space there. So far, we have assumed that every page will be filled up 100%. That is not always the case. Okay. So in all of this calculation, we have assumed that all of the pages are always full, but that is not always possible, right? So let's say in here you have inserted 10, 20, here you have 15, 17, here you have 12, right? So all of those data are in here, but then you deleted some data, okay? Or you made some update, you made some changes, you inserted some other data as well. So not all of the pages will always be full, right? Hopefully that part is making sense. Another case might occur why those pages might not always be full is because of the search. We sometimes, when we insert the data, we sometimes employ some strategy, like the first page will contain data from, let's say, 10 to 20. Let's say the student mark I am storing, whoever got from 10 to 20, those students' data will be inserted into first page. So from 21 to 30, let's say we'll go to the second page. Okay, so that's what the assumption could be. Okay, so that's why now you can see that if I am calculating this, so there will be varying number of students. So in here, there could be 2 students, in here, there could be 10 students. So not all of those tables, pages will always be full. Okay, so that's why we have an assumption in here. Let's assume that pages are on average 75% full. So on average simply means you know that some are 100% full, some are 50% full, something like that, right? So we made an assumption that these pages could be 75% full. Okay, so if that is 75% full, then how many record can we store? So we have previously calculated that we can store 19 record. If the pages are on average 75% full, then we can store 14 record per page. So at that time, we have to calculate using this 14 that we have, right? So 2 million record divided by 14 record per page. If we divide, then how many pages do we need? That is what we can calculate. If we want to calculate the overhead as well, so overhead will come up as like 47%. Now we can see that is definitely true, right? Because we are wasting 25% space in almost all the pages. So that's what the assumption is. Hopefully this part is making sense. Yeah, that's what the initial space calculation is. Okay, how many pages we need, how many record we can store in a page. Any questions? Someone is asking, is there any calculation like this in the final exam? Yep. There could be something like this in the final exam, where this could be a final exam question, right? So you will have table size, you will have general features, and it might be asking something like this. How many bytes per record, how many record per page, how many pages for storing the table, let's say. If there is some assumption that will be given to you, it will say that assume that all the pages are, let's say, 80% full. Okay, so all assumptions will be there. If there is no assumption, that simply means that always the pages will be 100% full. Okay, so this is what the calculation will be at that time. Any other question? Someone is saying, if a page is 75% full, then it uses, no, you got it wrong. So 200 byte was the size of one record. So you confuse that one, these two. So 200 byte was the size for each record. And now I am saying that each page is 75% full. Those two are two different things, right? So how many record I can store in a page? Now, when I'm making an assumption that they are 75% full, right? So in this case, I can store 19 multiplied by that 75% that we had. Hopefully that is making sense now. Yep. Yes, that's what the calculation is in here, right? So 19 record per page into 75% average occupancy that we have. Any other question from anyone? So this is the first part where we are simply calculating how many pages do we need. Later we will see to search from these pages, how much cost do we have to bear. No question? Okay. Let me move forward. Okay, so now we have some idea regarding the space requirement. Now, how the record will be stored in a file. So when we are trying to store this record in a file, they could be stored in an arbitrary way. Arbitrary means there is no order. Whenever the data comes, we simply insert that data, right? So that simply means unordered data, also known as heap files. Okay. So this simply means a record can be placed anywhere in the file where there is a space. So whenever someone is trying to insert some data, we'll look into the file, wherever there is a space, we'll simply put it there. Okay, so no ordering, no calculation. So insertion should be very easy. Second could be sorted data. Sorted means we'll always keep the data in a sorted format. So if someone gives me, let's say 25, I need to figure out where should 25 go. Okay, where should this mark go in my file? So we first need to figure out where is this space, then we need to empty the space and then put the data there, right? So that's what we have to do in sorted file. Now you can understand that for inserting or updating for sorted definitely takes some time rather than the unordered one. But why we will do that? Because that will help us with search. Okay, we'll talk about that one later. Another could be index. So index is like a tree-like structure. Okay, we'll talk about that today. Index. If you are not familiar with tree, that's fine. Don't worry about that. I'll talk about that one in detail today. Okay. So either unordered or sorted or in an index in a tree-like structure, we'll store the data. So if data is unordered, when that one will be helpful? So think about, we are running a query, select star, right? So select everything. When I'm writing a query like that, select everything from student table. At that time, order doesn't matter, right? So wherever the data is doesn't matter, we can simply print out everything. So when we are trying to retrieve all the record, at that time, this sort of file structure will be helpful. Sorted. It can speed up search. Definitely understand that because everything is sorted, right? So we can find the data quickly using binary search. If you're not familiar with binary search, don't worry, we'll talk about binary search today as well. But if you are familiar, you already know that binary search is much more faster, okay, because the data is already sorted, but update could be expensive. Update simply means insert, edit, delete, those sort of things, right? So like I said, for inserting any data, you first need to figure out where the data should go. So that one will be much more expensive than this unordered one. Index, this tree-like structure that we'll see today, it is like sorted file. They can speed up the search that we have, okay? And here we'll see the update will be much more faster than this sorted file that we have. I'll just give you one hint that in this case, the data is physically sorted in the physical storage where we have the data. There, the data is already sorted. In here, the data will be logically sorted. So that is the difference between these two. Okay, what does logically sorted means? I'll talk about that one later. But the main difference between these two is, first one, the sorted file is physically sorted. When you look at the data, we'll see that everything is sorted. But in index, we'll see the data is unsorted. But when you go inside, we'll see that everything is actually sorted using the tree-like structure that we'll have. Okay. Yeah, so if we store the data in any way, unordered, ordered doesn't matter. So which search technique we should use to figure out the output of our query, right? So for depending on the architecture, depending on how we are storing the data, we might use different sort of algorithm or process. Okay, so if the data is unordered, that means they are stored in a heap file. So heap simply means unordered data. Okay, at that time we have to use linear scan or linear search. If the data is physically sorted, then we can use binary search. If we have index created, then we can use index search. Okay, we will talk about these three in detail. So let's start. So access path, that is simply means which access path you are using. That simply means which technique you are using in which case. Okay. Okay, so let's think about this query. That select everything from a student where SID equal to something. We want to figure out the output of this query. Okay. So depending on the structure, how the data is stored, unordered, physically sorted, logically sorted. Okay, so whatever the structure is, depending on that one, definitely we can understand that the output will always be the same. Right? Select everything from student where SID equal to this. The output, it doesn't matter which process you are using, the output will always be same. What will be different? The execution time. How quickly you can get the output, right? So that one will differ. So that is the first thing to understand. So that is what is written here. So it has no effect on the semantic of the statement, whichever technique you use, but it has a major impact on the execution time. How much time will you need to figure out the output of this query? Okay, so it doesn't matter which one you are using, the output will always be there, the correct output, but the time will differ among these techniques that we have. Okay, so let's start with linear search. But before going there, one thing to clarify is what is the meaning of cost? that we are going to calculate. So we have this idea that data is already sorted in the hard disk, but to make any operation, to perform any operation, we need to transfer that data from hard disk to the main memory, right? And how do we transfer? So we transfer one page at a time. So the page is the unit, that's how we transfer. So we'll always transfer one page from hard disk to main memory, or if we need to write the data, then we'll send one page from main memory to hard disk. So that thing is known as input output IO operation. So reading or writing a page. So that's what we are going to calculate, because that is what the main cost is, okay, rather than the cost of actually calculating the thing. Okay, so let's say I want to simply sum up to number. Okay, so we first figure out where that number is in our hard disk. We need to get that data from there, put it into main memory. Then simply doing the addition takes very less time compared to that transfer time that we have. Okay, so that's what we are actually going to calculate. So the cost of SQL execution is usually measured by the number of input output that we need. How many transfer do we need to answer a query? So that is what we are going to calculate today as well. Okay. Hopefully that part is making sense. So simply we are going to calculate on the cost. We are defining cost as the number of input output that we need from our hard disk to main memory. How many pages do we need to transfer between these two memory that we have? Okay, so let's start with linear scan. Let me open up another one. So linear search, first I will go through very simple examples, okay, so that if you're not familiar with linear search, you know how linear search works. So linear search, simply think about that we have some data, okay, stored somewhere, and they are unordered. So here we can see that nothing, no order is there, and we want to figure out, let's say 16 from here. So how can we figure that one out, right? So that is what linear search will teach us or tell us. Since data is unordered, only option we have is to go through each of the data one by one, right? It's starting from the first position. So we'll start at the first position. We'll have a look whether this is 16. First data is 80. No, that is not 16. So okay, move forward. Is this 16? No. Is this 16? No, no, yes, right? So you got the data, you can stop there. So the technique is simply starting from the first position, check every data. If that data is there, return yes. If the data is not there, return no, that data is not there. So if I'm looking for 50, when can I say that 50 is not here? Only after checking all of this data, right? So we can see that 50 is not here, but the system will only be able to answer that one after comparing all of these things. So how many comparison do we need? So in this case, if we have 1, 2, 3, 4, 5, 6, 7 data, right? So after making 7 comparison, then linear search can tell us that no, 50 is not there. So if we have n number of data, so it will need n comparison. So that's what is written in worst case. So for linear search, the worst case is when the data is not there. So in the worst case, we need n number of comparison, hopefully making sense. So only after comparing n time, we can say whether one data is there or not. Also think about cases where data could be repeated. So if 16 could be in this data multiple times, think about that is not a primary key. You are looking for mark. Which student got 50? So more than one student can get 50, right? So at that time, if you are using linear search, what you have to do, you have to keep going. So even if you got 16 in here, you can stop, right? So another student could have 16 as well. So when you are looking for 16, you cannot stop. So you have to go through the whole data. So hopefully that part is making sense. But if it is, let's say, a primary key, you are looking for student ID. Student ID is a primary key. That data will be there only once. So when you got the data, you can stop. So those sort of things we are going to calculate later. Okay, if it is a primary key, what will happen? If it is not a primary key, then what will happen? But hopefully linear search is making sense that we'll need n number of comparison to figure out the data that we have. Okay, so if we perform this operation n times, how many searches we need? Let's say that if I am looking for 80, I can simply figure that one out in the first position. That simply means only one comparison, right? So if I am running this linear search n number of times, how many comparison do I need? That's what we are calculating. So let's say for the first time you figure out the data is in the first position. For the second time you figure out the data is in the second position. That's how you can calculate that for nth search you will need n number of comparison. So how many comparison or search do we need in total? So we know this calculation, right? So 1 plus 2 plus 3, this series. The equation is n into n plus 1 divided by 2. That was the equation is, right? So on average, how much do we need? So if we divide this one by n, so on average, if we divide this one by n, because we run n number of searches, then it comes up at n plus 1 divided by 2. Hopefully these calculations are making sense. So in the worst case, we need n comparison. On average, for linear search, we need n plus 1 divided by 2. That means simply half, right? So that many comparison we will need on average for linear search to figure out whether some data is there or not. So that is what is written here. So when we are using linear search, also known as file scan or table scan, where the data is totally unordered. So on average, we'll need half of the pages to read. Okay, so that simply means we need to transfer half of the pages. And in the worst case, we need to scan the whole file, right? So how many pages we have? If we have n number of pages, we have to transfer everything that we have. Hopefully this part is making sense. So from here, need to remember for linear search, in the worst case means if the data is not there or if the data can be stored there multiple times, at that time we need to transfer all of the pages. But on average, we will need half of the pages to be transferred into the main memory. Someone is asking, total number of search means the time you need to find out all the data. Yep. So total number of search means if I run n number of searches, let's say 3, how much time do I need in total? Or how many comparison do I need? Not time actually. Okay, so let's think about this example now we have. So in linear search, we are trying to apply linear search. So in here, how many pages of IO do I need to find a record for this query? Hopefully you remember the structure of this table. So relation was the name, tuple key was the primary key, if you remember, right? So this is the primary key. We have this many pages for this table, okay? So we want to figure out how many page IO do I need to find record for this one, where the data is stored arbitrarily, okay? There is no order there. So few things to notice. First, we are looking for a data where the tuple key is primary key, right? So primary key, what does that mean? So it means that it can appear only once. Once we get that one, we can stop. Also, we have equality sign, right? So this is primary key and equality sign. So equality sign simply means that when we find 715, we can stop there. Think about if we had, let's say, greater than 715. So if the query was where tuple key is greater than 715, so we then need to keep going, right? So we need to check all the data whether they are greater than 715. So we cannot stop, even if we are running a query on primary key. But since we have a primary key and the equality sign, we can stop whenever we get the data. So that is what is written here. So equality, when we have equality, that is known as equality search. And in this case, tuple key is unique because of the primary key. So we can stop at the first match that we find. So if the record is there, in our table, then on average, we need to transfer n plus 1 divided by 2. So n simply means number of pages plus 1 divided by 2. So this many IO operation do we need. If the record is not there, right, or if we are running any query on non-unique attribute, at that time we have to check every record. That simply means that we have to transfer all of these pages. Hopefully that part is making sense. If we don't have equality, let's say the query is figure out where attribute between 100 and 119. Can anyone guess how many pages do I need to transfer for this query if I'm using linear search? This is the total number of pages we have for this table. Yep. Few people answered and all of them are right. So first thing to note is that this is a non-unique attribute, right? And there is a between condition in there. Between means 100 and 119. So you cannot stop at finding 100. So you have to go through the whole pages to figure out whether every record is between this range that we have. So this sort of query is known as range query or range search. Okay, so at that time with linear search, we have to transfer all the files that we have, all the pages that we have. Making sense? Linear search, that's about it for linear search. Okay, so we'll look into what is it that we are looking for. Okay, so whether that is the primary key or not, and whether the condition is equality or any other condition is there. Depending on that one, we'll have. Yep, someone is saying, what if the page is this, then divide by 2 on average? That is not an indicer. So the main question is, what is it that we are going to take? The floor or the ceiling? So ceiling means the top part, the floor means the lower part, right? So we'll always take the upper in here, right? Because we don't want to find leave out one page which might contain the data. So if it comes up at, let's say 2.5, so we'll definitely transfer 3 pages in that case. So it will always take, this one is known as ceiling. Okay, so we'll always take the ceiling from there. Any other question, anyone? So that's about linear search. Definitely not a very good search, right? Because we have to go through the whole data. So there are some drawbacks. This is extremely slow for large tables. So just to show you how slow this technique is. So I have a table which is of huge size, 1 petabyte. Petabyte simply means 10 to the power 15 byte. Okay. And we are using the fastest drive that is available, which is solid state drive or SSD. That is the common name normally we use, right? So that is the fastest right now we have, and that speed is 6 gigabyte per second. So it can transfer 6 gigabyte per second. So if we are using linear search, how much time do we need to scan or go through this whole table, which is of size 1 petabyte? Okay. So you'll be amazed to see the calculation, right? So if we have this many bytes and we can transfer 6 to 10 to the power 9, which is gigabyte per second, and we multiply that one to convert into hour, days. So it takes 1.9 days to go through this table that we have. Okay, so around 2 days we will need to answer a query from this table. So if you write a query on this table, select something from this table where there is a condition, you have to wait 2 days, around 2 days to get an answer from that. Okay, this is definitely not working. Takes too much time. Definitely want to reduce that. What is the way to reduce that one? It's to make the data sorted. Okay, when we are inserting. Okay, so we'll sort the data so that we can speed up the search, okay, so that we don't have to wait 2 days to answer a query. So we'll always keep the data in an sorted order, either increasing or decreasing, that doesn't matter, okay, but the data will always be sorted. Okay. If the data is sorted, then the technique that we are going to use is known as binary search. Simply think about how you find a word in a dictionary. If I give you a dictionary and ask you to figure out a word, how do you figure that one out? What I normally do, I open up any page. Let's say I'm asking you to figure out what is the meaning of university. Okay, so if I open up a page and it shows me the first letter is P, then I know that in left side university is not there, right? So I only have to look on the right side of that page that we have. So that is what binary search means. So let's go through binary search first, then I will talk about the rest of the things here. Binary search, the first assumption is all the records are sorted. How we'll keep that sorted, we'll talk about that one later, but first assume all the records are sorted. And from there, I want to search for something. How many comparisons do we need? In linear search, we have to go through each one of them, right, one by one. But for linear search, we don't have to do that. We can go in arbitrary position, but there is a process. We'll not go to arbitrary position, but we'll go into the middle position that we have. So this low and high is simply showing where the minimum number is and where the maximum is. So minimum is in the 0 position, maximum is in the 14th position. The data is, right? So what is the middle? 0 plus 14 divided by 2 is 7, right? So 53 is my middle element there. What is it that I'm looking for? I'm looking for 33. So without making any comparison with any of this data, I can clearly say that 33 will be on the left-hand side of this middle position. I don't have to compare with all of these things. So I can simply remove them. Right? So I don't need to compare with all of these, simply means that I don't need to transfer these pages. Right? So now we can see that after simply making one comparison, I was able to divide that one by half. Number of pages that I have, I can divide that one by half. That these many pages I don't need to transfer. Just transferring this one, I'll compare with 33 and 53. 33 is less than 53, so I know the data will be on the left-hand side of 53. Keep doing this process again and again unless you are done. Done means you got that data or there is no data. Okay. So repeat that process. Now the low is on 0, high, this is the maximum position that we have, 6. Again, 0 plus 6 divided by 2 is the third position that we have, right? So again, we are comparing 33. Here I have 25. We know that data cannot be in the left-hand side of 25, so we only keep the right-hand side that we have. Okay, so how many comparisons we made? So far we have made only 2 comparisons, but we are able to remove all of this data or all of these pages we don't need to transfer. Now we have this amount of data. Again, do the same process, figure out the middle. Okay, so where would be that data? Will be in this position. Now we can see that if we compare 33 with 33, we know that 33 is there. If let's say 33 was not there, you are looking for 30. This is 33. Since low and high are at the same position, you know that they are pointing to the same position. That means we can stop. Right. So since luckily we have 33 in here, so we can simply transfer this one. So how many comparisons we needed? In this case, only 4. Yes, right. So first we figured out this middle position. So I simply have to compare 33 with 53. Later I have to compare 33 with 25. Later I have to compare with 43 and finally with 33 and 33. So I simply needed 4 comparisons. That simply means I have to transfer 4 files to make that comparison, right? So comparison is operation. So to make any comparison, any operation, I have to transfer that one, right? So that's what is written there. Yep. So we got 33. So how many comparisons we need? Log 2 base n. Hopefully that part is making sense. If not, let me know, I can go deeper, but hopefully this is very simple, right? So every time we are dividing the thing by 2. So that's why we have log 2 base n number of comparisons. So if we have 14, so we'll need 4 comparisons from here. Think about when you have 100 data, after one comparison, divide that into 50, right? So from 50, it gets divided into 25, then 12, that means 13, 12.5 is 13, right? So that's how it becomes smaller till it becomes 1. So in the worst case, in binary search, okay, then we need log 2 base n comparison. No. Yep, so we got it wrong. Someone is asking, how does the search know that position 4 has 33? So he doesn't know in which position we have. So we simply figured that one out by always calculating the position of this 33 that we have. Okay. So he's not checking there one by one. What he is doing, he's only comparing 53 with 33. That is the first comparison is. Okay. So you compare 33 with 53. Is it the same value? No. So is it less than 53? Yes. So you will look into all of this data, right? So that's what I said. You remove all of these. He now knows that this is my search area where I have to search, right? So again, the same process will continue. We'll figure out the middle among these. Yep. Then we'll compare 25 with 33. Then we'll keep doing this process unless we find the data. So when 33 is in the middle, at that time 33 will be compared with 33. At that time, we will know whether that data is there or not. Hopefully this part is making sense. How do we search using binary search? Only thing left is how do we ensure the data will be in a sorted order, right? So if the data is not sorted, this one will not work. Now you can understand, right? So if this data is not sorted, then this assumption that we are making that it will be on the left-hand side after making one comparison, that is not true if the data is not sorted, right? So the first thing to ensure is the data is the sorted format. So how do we ensure that? So let's say I have a data like this, and I now have to insert 20. I cannot insert 20 at the last position, right? So I have to insert it into its correct position, which is between 14 and 25, right? So we can again run a binary search to figure out where 20 should reside. Okay, what would be the position of 20? But let's say in this case, we figured out that in this third position, we have to insert 20. So main thing to note is what we have to do once we figured that one out, that in the third position, we have to insert 20. So what does that mean? That simply means that we have to push all of this data that we have. So 97 should go into 15th position, 96 should go to 14th position. So all of them should move. That is the first thing to understand, right? So this one will take huge time. So to insert one data in one position, we have to move all the pages, all the remaining pages that we have. So think about, I am trying to insert 5 in the first position. That simply means all of these pages needs to be pushed back. So this is huge cost, right? So we have to push all of the pages. So we have to work on all of the pages. So insertion, or that means any update that we have, takes a lot of time. So once we move all of these, only then I can insert 20 in here. Okay. So this is not only for insert. Think about edit or delete. So if I delete something, let's say I'm deleting 51, that simply means I need to push everything forward. So if I remove 51, then I need to push 53 into 6th position, 64 into 7th position, right? So I have to push forward everything. Even if I update some data, if 14 becomes 80, what will happen? Then this data cannot be here. So we have to find a new position for that one. We have to go there, push it there, and then push all of the things that we have, right? For binary search, to keep everything sorted, doesn't matter whether it is insert, edit, or delete, for all of these cases, we have to sacrifice a lot of cost there. Hopefully that part is making sense. Yep, so all of those things are written in here that I try to explain using that example. Someone is saying, how it know where to insert? Should inserting also be compared with the middle? Yep. So where to insert? We can find this position, right? We can find it position using binary search as well, where we need to insert. So any data which is less than the data that we are trying to insert, from there we can insert, right? So we have algorithms to do that. So to 20 should be between 14 and 25, right? So why? We definitely can understand that part, right? Because 14 is the maximum lowest number from 20, and 25 is the smallest maximum greater number than 20, right? So if we figure that one out, then we'll be able to figure out where 20 should be there. Okay. So for the time being, don't worry about how we figure out that position. Think about using an algorithm. We'll know which position we have to insert, but the main thing is we have to push everything there, right, to keep it sorted. So the same example we can think about in here in terms of database, right? So in a database, there will be stored in a page. So in a page, there could be multiple records. So that's what this one is saying. 11, 12 means more than one record in each page. Okay, we have. So if we are using binary search, then we know that IO cost will be log 2 base B, where B is the number of pages that we have. Plus, if we need to transfer any pages which contains the retrieve record as well, right? So if you are looking for something, let's say greater than 100, the query is saying where mark is greater than 50. So you figured out where 50 is, right? So you find that page, and from there you transfer all the remaining pages, right? So if in this case we are looking for greater than 50, right? So we need to figure out that this one is the data. From here we need to transfer all of the pages, right? So that's what is written in here. Log B plus the number of pages that might contain the retrieve record that we are looking for. Okay, but this is the main thing, how many comparison we need to find the first record that we will have. After that, how many pages we need to transfer depending on how many data we have from there, right? So the same example that we have seen for linear search, if we have this number of pages, then we can see that after 18 comparison, we can answer that query. But previously we had to transfer all of these pages, right? Or in average case, I have to transfer this one divided by 2, but that one was still 70,000. But now we can see that after 18 comparison or after 18 transfer, we can say what will be the cost, where the data is, right? So that's how binary search helps us in figuring out the output of a query very quickly compared to linear search. Yep, here is the example that we have. Someone is asking, can you give us an example of the IO cost? So this is the IO cost that I need. So I need to transfer 18 pages. So previously we needed this many pages, but right now this is the one 18 IO cost I need for binary search where I have this many pages. No, this one will not know, right? Without looking at the actual data, we'll not know how many extra pages do we need. So that's what I say. We'll only focus on this part to figure out the first record that we have. From there, how many do we need? We can simply keep transferring the file, right? But that depends on the data we have. Someone is asking 140351 starting from 0 or starting from 1, does it matter? So this is total number of pages I have. So if I'm starting from 0, then last page number will be 140350. If I'm starting from 1, the last page number will be 140351. Right? So that has no effect. I simply need to know how many pages do I have. So in this case, these many pages I have. So indexing have no issues in here. Hopefully that part is making sense. Any other question on binary search? None. Okay. Drawback, we have already seen that it is very expensive to maintain that sorted order when records are inserted or records are updated or deleted. Someone is asking, how can I know if data is sorted? Yep, that is the first assumption. If the data is not sorted, then you have to use linear search. If the data is sorted, only then you can use binary search. So when you are inserting the data, how you are inserting, that's what we need to know. Right? So if we are inserting the data in a sorted way, we know that data is sorted. At that time, to search any data, we'll apply binary search. Otherwise, we have to use linear search. So like we have seen, maintaining the order is very, very expensive. Okay, so we might have to shift all the subsequent record to make a space for the new record, like the example that I have shown you. Okay, so same thing. Let's say this is our data. I want to insert 2. So what do I have to do? I simply have to move all of these. So 3 will go to the next page. 5 will go in here. 7 will move into a new page, right? So you can see that I have to transfer all the pages and make some changes there. So that part is really difficult with binary search. Okay, so that's why sorted files typically are not used in DBMS system. Okay, although it gives us very good result with searching, but it gives very poor performance when we are updating data. So how actually DBMS saves everything or does that processing is using indexing. Okay, so it speed up the query processing via indexing. What does indexing means? You have already seen indexing. Let me show you an image first, then I'll talk about this. Have you ever seen anything like this at the end of a book? Yes, definitely. Right. So the name was there, index. How does that help us? So when I'm looking for something, let's say I'm looking for this one, Brownie William. So this one is somehow saying that Brownie William, this data you will find in page number 14. So if I know that, I simply need to go to page number 14. I don't need to look into any of the pages. I don't need to do any comparison or anything like that, right? So if there is an index, that index might say that data is in multiple positions. Like in this case, we can see that this one is saying that this data is in 140 to 142 page, also in 167 page, right? So there will be an index that will somehow tell us how that, or we'll figure that one out, right? So that is what the idea is in here. So we'll have a magic box. Okay. Whenever I'm trying to find something, let's say that is not a search key, I'm trying to search something, I'll ask this magic box. This magic box will tell me your data is in these 2 pages. So what do I have to do? I simply need to transfer those 2 pages. And in that page, then I have to look for the data. Okay. How do we create that magic box? That is what the discussion will be. But hopefully you got this idea. Index is nothing but some things there which can tell us where your data could be or where your data is. Okay. So in this example, we are simply looking for age equal to 10 for the people who have age equal to 10. So this index is telling us that this data resides in page A and page H. So we go there, we open up or we transfer that to pages, we look through all of the record and simply figure out, okay, in here, the first one, in here, we have 2 records where the age is equal to 10. Okay. Someone is asking, is index a page as well? Yes, we have to store them, right? So you always store these indexes at the end of the page, at the end of the book. So those are stored in a page as well, right? Good thinking. So that's what we are going to calculate, right? So index will definitely take some space. How much space it will take? So index is nothing but a structure, data structure mapping search key value to a set of record in a table. So like in here. So search key, if search key is this name, it shows us, it points us to the right direction. Then go to page number 14, there you will find the one, right? Although the name is search key, but it is not a key because previously we defined key as something different, right? So key means it will be unique, things like there. So search key doesn't mean that. Okay. So search key simply means the thing that we are looking for. So that is what search key means. It doesn't mean that it will be unique or something like that. Okay. So that is what written here is not the same as key of a relation. Search key simply means the data that we are looking for. Okay. So think about, we have a table product. There we have name, maker, and price. Name is the primary key. We have whatever you are looking for. If you are looking for name, if you have an index based on name, then you can find the data. Now think about if you have an index based on name, but you are looking for price. Will that help? Definitely not, right? So that is what the issue with indexing is, but we'll go there. And indexing provides an efficient lookup and retrieval by search key value. Definitely, if we have everything in as an index, we can quickly go there, right, and figure out the data from that page. Typical index type that we have is hash index. This is typically used for equality search. B+tree index is another one, which is very good for range search and also can be used for equality search. today we'll only talk about B plus tree search, not hash index, because this one you can use for both equality search and range search. But before going there, what is the disadvantage? Every system will have some disadvantage, right? So first downside is it will take additional space. In a book, when we have index, so we have extra few pages, right? So the book could be 500 pages, but the total size, because of this index, which takes up another 10 pages, 510, right? So this one will take up space. It will be efficient though to finding the data, but the problem will be we have to change the index when the table is modified. Think about if I insert a new page in this book, then all of these numbers becomes invalid, right? So I have to update all of this index from there. If I simply insert one page in this book, then this one should be increased by one, all of this, right? So we have to update the index whenever the table, the actual table gets modified, okay? Depending on the index, which one we are using, it could become very costly as well. However, indexing is very efficient, and that's what DBMS use. Most of the DBMS that we have, okay, so they uses indexing technique. And today in your tutorial session, your tutorial show you how to figure out that indexes for your tables that you have. Okay, what command should you use? Your tutorial show that. Okay. Yep. Someone is asking for break. Yep. This is where I will take the break, and then we'll talk about B plus. Okay. So let's take 5-minute break. Then we'll come back, and then we'll talk about B plus 3. In the meantime, if you have any question, write that in the chat box. When I come back, I will answer. Okay. Okay, I'm back. Hopefully everyone is back too. Someone is asking for the binary search. You don't understand why it would be more than log2. Yep. So think about, in this case, I'm looking for not 33, but all the values which is greater than 33. Okay, so at that time, what do I have to do? So if the query is where mark is greater than 33, so first we figure out 33, right? Using log2 base n. So this number of comparisons, we need to first figure out 33. But from there, we need to transfer all of this data, all of these pages that we have. So that is what that plus number of pages was, right? So we might have to transfer extra pages depending on the query that we have. Hopefully that part is making sense. Okay, hopefully everyone is back. So B plus tree index, how do we create the index? How do we keep everything nicely in there? So like I said, so in this case, the idea is that the data will be logically sorted, okay? Not physically sorted, but logically. So there will be a logical connection. So what physically and logically means, so this is what physically sorted data means. So when you look at the data, we say everything is sorted. In here, we are seeing everything is sorted, but there is some link between them as well, right? So these links will play a vital role now, okay? So think about, if I want to insert 2 in this case, then what we will do, because of this link, what we can do, we will not change anything in here. But since I need to insert 2 in this first page, what I'll do, I will move out 3 from here, right? So I'll move out 3 to, let's say, in the last page, there I'll create, there I'll push 3, and then I will insert 2 in this first page. Now we have. So now when I look into this data, now we can see the data is 1, 2, 4, 5, 6, 7, 3. That is what physically the data looks like. So this is unsorted. This is not sorted, right? But because of these logical connections now we have, now this one is saying from 1 to you can go to only this place, which is 3. Then from 3 you can go to 4, 5. From 4, 5 you can go to 6, 7. Right? So this time we have this link. Although the data is physically not sorted, but because of this link that we have, so data will be sorted. So this one is known as logically sorted data. Okay. So how do these links work? If you are familiar with linked list, the term linked list, then that is what I'm talking about. Okay. If you are not familiar with linked list, so linked list simply means that there will be link between two data, between two consecutive data that we have. Okay. Just to make you familiar with linked list, if you're not familiar with linked list, so in linked list, we normally have a head. Head simply is what is the first position of the data, so that we can start scanning the data from there. So when I have no data, head will point to null. Null means there is no data there. Okay. So let's say I'm trying to add 50 at the end of the list that I have every time. So for case 1, when I have no data, I simply insert 50 at the end. So since 50 will be at the end, that will point to null, then I simply need to change this pointer that I have. Okay. Someone is asking, is head specified in the search? Yes. So we'll always know where is the value of head. Okay. It is not always 0, but head can point to any position, but from there we will go through the whole list. Case 2, where we have some data. Case 1 was when there was no data. Case 2, we have some data. We still want to insert 50 at the end of this list, right? So since we want to insert 50 at the end, so 50 will point to null. That's what we know. But now we need to figure out which one should be linked with 50. The problem with linked list is that we simply have to always start from the head because we don't know the link, right? So from 3, which is the next data, only 3 knows which is the next data, right? Because of this link. So 3 knows that my next data is 17, 17 knows my next data is 12, so things like that. So we have to go through all of them one by one. Once we are at 12 and 12 is pointing to null, now I know that this is my last data and I'm trying to insert new data 50 in here. So I need to update this pointer now. So I simply update this pointer to 50. Now you can see there is list looks like 3, 17, 12, from 12 go to 50, then go to null. Right? So I don't have to change the position of this data, only this link I need to change every time. So this was the first case where I was always inserting at the end. Let's say I'm trying to insert at the start. Same two cases will occur. If there is no data, what I have to do, 50 will point to null and head will simply point to 50 because that is my first data. If I have some data, there I am trying to insert 50 at the first position. What do I have to do? I have 50, right? So where will 50 point now? Where current head is. That's where 50 will point. And then I'll simply change this pointer of head to 50, right? So now you can see the list will, if you start from head is pointing to 50. So that's where you start. So 50 has been added into the first position. Other cases like if we're trying to insert somewhere in the middle, not at the start, not at the end, but somewhere in the middle, let's say between 17 and 12. So you have a node 50, you want to insert that one between 17 and 12. Now you know what you have to do, right? So only thing that you have to do is, since this is between 17 and 12, so 50 will point to 12, right? And 17 will point to 50. So main thing is to note from here that only these links get changed. Right? So not the actual values, not the actual position, but only these links that we have, logical links, that one will get changed, and that's how we have new list from there. Same thing for delete or update as well. So if I want to simply delete this one, 50, then 70 will simply point to 12, wherever 50 was pointing. Hopefully you got some idea. Someone is asking, is order necessary? Depending on if you are creating and sorted, then order is necessary. But in this case, I was not thinking about order, simply how to insert any data in a linked list. But in B+T, we'll have an order. How we'll maintain that, I'll show you later. Okay. Someone is asking why there are two numbers in a block, not one in a block and linked. Yep, so this one is simply showing that is a page, and in a page there could be multiple data. That's what this one is showing, right? So this one is simply showing here I have one student with let's say SID1, SID2, okay? So each page have two records in there. That's what this one is showing. Bad news, since data is not physically sorted, we cannot do binary search. For binary search, data have to be physically sorted. But since data is not physically sorted, but logically sorted, right, we cannot apply binary search. So what do we have to apply? We have to apply linear search. Okay. So we'll create index on this data file, and from there, we'll start working. So what does that mean? So first we have to create a logically sorted data file. Okay, so logically sorted data file simply means that the data in the first position will always be smaller than the data in the next position that we have. Okay, so that one is written here. All records in page I have a smaller search key value than all pages in I+1. So that is what sorted means, right? But since this is logically sorted, using this pointer now, we will always try to keep that sorted order there. We call this one as a logically sorted data, okay? But these pages may not be consecutive on disks like we have shown there. So one page could be here, another in here, another in here. So in the memory, it doesn't matter. So from this could be the link, and they are not consecutive in the memory as well. Okay, so when we have to create the index, okay, so the simple thing that we can do is that let's create one index per page. So for each page, we can create one index entry. So how many index do I need in this case? So I have this number of 140,351 number of pages. So these many indexes that I have to create, right? So if I want to create one index for each page, okay. So index, how much space does it take? If you remember that book example that I have shown you, it needs to have two things. First one is the search key and next one is the pointer. Two things I need. First one is the search key, Brown Williams, and then 14, in which page I need to go. Right? So in an index, there would be two things. First one is the search key and next one is the row ID, in which row or in which page I have that data. Right? So to store that, let's assume search key takes up 4 bytes and this row ID or the pointer takes up 4 bytes as well. So one index will have 8 bytes. That's what the initial assumption is. Okay. So for each of these pages, we'll create one index. So how many index we are creating? These many indexes we are creating. Okay, and each one will have 8 bytes. So how many extra space we need? We can calculate that one, right? This one multiplied by 8 bytes. So that many space to be we will need. So like someone pointed out before that this index need to be in pages, definitely. So we know that everything needs to be stored in a page, right? So this index that we are creating, this many index we are creating, we have to store them in a page as well. So how many pages do I need? Same calculation. We know that one page is 4 kilobyte, right? So in this 4 kilobyte, 250 bytes are always reserved for header data. So we will not be able to use that. So if we simply subtract that one, these are the empty space we have. Okay. Each index takes 8 bytes. That is the information we know. If we put them, keep putting them, simply dividing all of those, the same equation that we have calculated, right? So this many byte per page divided by 8 byte per index entry. So in a page, we can have 480 index. So how many pages do we need? That's one we can calculate from there. Hopefully this part is so far making sense. So we have just calculated one page can contain 480 index. If we have assumption like this, that not all of the pages will always be full, like we assumption we make for when we are storing the table. So again, if you're making an assumption that all the pages will be 75% full, that simply means each page can have 360 index. Okay. So number of index pages, we need this many indexes we have created. These many we can store in one page. So how many pages we will need? 390. Right? So if we simply divide them up and round it up, like I said, we'll always take the ceiling. Right? So this one will come up as 390. So this is what we have created. So this one is the actual data that we had. And then all the indexes that we have created, we will store them in 390 pages. Yep, someone is asking why 75%. So that was the assumption that we had, that some pages might be empty because we deleted something, okay, or we updated something. Okay. So not all the pages will always be 100% full. Some pages could be 100% full, some pages could be 75%, some pages could be 50% full. So on average, we assume that each page will be 75% full. Okay, so we can stop here, okay, with creating the index, but for the efficiency of the search, we'll keep going unless we have only one index page, okay? So we can stop in here, or we could store them in a logically sorted file and recursively build the index. Recursively simply means doing the same thing again and again. Okay. So if I keep doing this thing, what does that mean? Now think about this is the data file. This is the actual data, forget about this. So from there, we can create the index and we can create number of pages that we have, right? So that simply means creating index of indexes. So we have index page. So for each of the page, we will create an index. How many index we will create? 390. So how many pages do I need? Can anyone tell me how many pages do I need in this level to store all the indexes? Remember, one page can have 360 index. Someone say 2. Anyone else? One answer I got So yep, approximately 2. So we'll have to create 2. Yep. So someone wrote the equation as well. So yes, for 300 pages, for each page we create an index, right? And so this would be the equation, 390 divided by 360. So which is approximately 2. That means we have to create 2 pages in here. Like I said, we'll keep continue unless we have only 1. So what I have to do, think about these are my actual data. From here, I want to create an index. So this one index, this one another index. For 2 index, I have to still create a page, right? So in there, I will have these 2 indexes. Now you can see this tree like a structure, right? So this is what a tree looks like if you're familiar with tree. So there will be a top node known as root, okay, root of this tree. At the end, these are known as leaf node, which have no other children. So children means in root, from here I have 2 children. We can see this node might have other children as well. This node will have other children. Okay. When some node have no children, those are known as leaf node. Okay, we'll have a root node. So this is what the tree looks like. So this is how we create a B plus tree for the index that we will have. So how many index pages we have created? 390 plus 2 plus 1, so 393 index pages we have created for this table that we have, okay, which is 0.2% increase in space that we have. Okay. So to store all of these indexes, that will help us to figure out an output of a query, right? So we have to increase the size by 0.2%. Okay, but how do this one helps us, or how do we calculate this thing, right? This was probably not a good example, but I will show you something from where you can try yourself. Okay, so this one, I'll share this link later with you. So here they have visualization for many data structures. Okay, so we talked about linear search, binary search, you can see those. Today we are only talking about B plus tree. Okay, so B plus tree is here. This is what I will show you. Someone is saying, what is the meaning of this? So this one is the increase. So this one was the actual page, right? So how many pages do we had? And this is the increase that I had, number of index pages. So these multiplied by 100 divided by the actual page that I had. So that one will give me the number of extra pages that we need in percentage. Okay, so how do we create this B plus tree? So I'll show you from here using examples. So when you are using this, I will share the link in the chat later. Okay, so you can manage this speed. If it is too high, you can make it lower so that you can see what is happening. Maximum degree simply means how many child we can have in one node. So maximum degree 3 means we can have maximum 3 child. Okay, that simply means that in a tree there will be 2 data. Okay, let me show you. Let's say first I'm trying to create a B plus tree where I have nothing. All right, let me make it a little bit bigger so that you can see. I'm trying to insert 20. Nothing is in there, so 20 is there. 0, 0, 2, 0. That's how they represent. Okay. Let's say I'm inserting 30. Still no issues is there. 20 and 30. Like I said, in one node there could be 2 data because size is 3. Okay. If I now insert, let's say 10, then what will happen? One node can take 2 maximum. So here I have 2 data, 20 and 30 in this node because of degree 3. Now, if I insert, what will happen? Let's have a look. So 10 will be inserted there because the degree is not there. Now you can see that he has created one index file there. Hopefully making sense. 20 is up there. The property now you can see the left hand side is less than 20. Right hand side is always either greater than or equal to 20. Keep inserting. Let's say I am trying to insert 15. Where that will go? So we'll compare with 20. 15 is less than 20. So that one will come up in here and there will insert. So this is where we'll insert. Okay, so try to insert few more so that tree becomes larger and we can later see a few other things. We're trying to insert 40. 40 will be there, but that thing could not be there, so we have to divide it further. Right. So let's say I am trying to create another label. So if I insert 35, okay, in here, someone is asking about the degree. Degree means number of children. So this node have maximum 3 children. Okay, one node, how many children it can have? Maximum. So that's what degree means. Okay. So now you can see that a tree-like structure is always there. Someone is asking why 20 and 30 going on the top of the tree? Because the condition was for B plus tree is that the left-hand side will be less than the value of the root and the right-hand side will be greater than or equal to the value. So when I had 10, 20, and 30, think about which one should go in the top. If I put 20 on the top, then the left-hand side is less than 20 and the right-hand side is greater than 20, right? Because that was 30. So that's why 20 was going up there. So same thing, if you're still confused, think about, let's say I have 35, 40, and I'm inserting 50, then which one will go on the top? 40 will go on the top. At that time, 35 will be less than 40, right? And 50 will be greater than 40. So that's what will happen. So if I keep inserting data, this is what happens, right? So first it will try to insert in here, but it will take 40 up there, and this is why this one will happen. Maximum degree 3 means now we can see that this node have 3 child, 1, 2, and 3. If I try to insert another one in here, okay, then you will see it will get divided, because at that time we'll need 4 if I insert another one. So it will be divided and that one will go on top. So you can try, okay. Main thing is once we have this sort of tree, how do we find any data? So if we are looking for some data, let's say 10. Now you understand, right? So how do you find that data? So if we are looking to find that data, first we will check with 30. 10 is less than 30. So it will go to the left-hand side. Now you can see the same thing like binary search, that we don't have to check anything with this part on the right-hand side of 30, right? Because the right-hand side of 30 will always be greater than 30, but I'm looking for 10. So if I'm looking for 10, it will go on the left-hand side. Comparing with 20, it knows that this node contains 10. So now he is saying that yes, in here, yes, found 10. If the data is not there, you are looking for, let's say 60, or let's say, so that we go right and left. So that one will be, let's say I'm looking for 38. So 38 is greater than 30, will go on the right, but it is less than 40 or greater than 35. So it will come up in here and try to figure out whether the data is there. Right, so we can see that it comes up in here, and in this page, he only checks whether the data is there. So this is the main data that we have, okay, and these are the index. Remember that. So if I'm looking for 30, so should I stop in here when I match that one with root? Definitely not. We have to go into the leaf where the actual data is. So these are index, okay. So when I'm looking for 30, you will see that it will not stop at the root. It will go through the whole process. 30 greater than or equal to 30. So on the right hand side, less than 35 goes in here, and then it says yes, 30 is found in the data. Right. So this is the actual data. These are the indexes. So we don't stop at index. We figured out the index is saying go to the right. From here, the index is saying go to my left, and you will have the data. Someone is asking, do we have to create one of these trees? No, it will not. Okay, so you'll never create an index like that. It will not take ages. But when you learn about some other courses like data structure, there you will create those. Okay. Yep, those are indexes. Those are not actual data that we have. Hopefully making sense. I'll share this link in the chat so that you can try later. Link is there. Many data structures are there, whatever you want to see, but today we only talked about B plus. Okay, you can check that one later. John just ran away. So this is what we have created. This is what I wanted to show from that example. Okay, that will have something like this, where the left hand side will always be less than 17, right hand side will be greater or equal to 17 from the root that we have. Okay. All of these last leaf node, they are the actual data pages. That's where we want to reach. So we know how to find the data. Hopefully now that part is making sense. Remember this thing, all the path from root to leaf node are of same length, right? So whatever data you are looking for, the length from root to the leaf is always same in B plus tree. That is the property of B plus tree. Okay, so in B plus tree, the length from root to leaf node are always same. So even you are looking for 2, you need to compare 1 and 2 comparison. Even if you are looking for, let's say 29, 1 and 2 comparison. Right? So in whichever way you go from root to the leaf, there will be maximum 2. That will be only 2 comparison there. Okay. So the length is always same. That gives us a lot of benefits. So how many comparison do we need? So if I am looking for 29, I simply need to compare twice. In this case 1, and this case. See, any data I am looking for, I know that it will take 2 comparison. Whatever data I'm looking for, even if it is there, even if it is not there. In this case, the tree that we have created. Okay, so if I am looking for the output of this query, select everything from relation where tuple key equal to 715. Right, so here I have an equality search on tuple key. We can use the index that we have created. So how do we compare that one? Now you know, you start with the root, right? Then root will tell me either go to left or right. So based on that, we will go to left or right. From there, this one will tell me whether I need to go to left or right. Let's say I'm going to right. From there, that one will take me to the left, right? So that's how it will start from root, go to either left or right, depending on the data you are looking for. From there, go to left or right, depending on the data, and finally figure out where the data is there or not. Okay, so always it will take 4 IO compared to this type of IO in linear search. Okay. So even if the data is not sorted physically, but we can see that to search, we need 4 IO operation only in this tree that we have created. What will happen if I am looking for a data where the condition is on attribute, but these index are created on this tuple key, this primary key that I have? Then how many IO do I need? Anyone have any idea? I'm looking for attribute, but the index is created on tuple key. Then how many IO do I need? Then this index doesn't help me at all, right? So using this one, I cannot do anything. So just to clarify, think about the book example that I have shown you again and again. So here you have this book, right? So all of this name you have, but I am asking you, find me the student who has got mark greater than 50. Does this index help? It doesn't help at all, right? So this index doesn't help at all. So that's what I was asking, that if I have an index based on tuple key, but I'm looking for another attribute, at that time, this index is of no use. That simply means that I have to transfer all the pages that we will have. Okay. Someone is asking, how does index change? For example, if I insert some information, how program will generate an index? Yep, good question. So think about, if you are inserting some information, do you need extra page? If you don't need any extra page, the remaining, the current pages that you have, you can insert the data there. No index need to be created, because we create index only for page. Only if you need an extra page, right? So at that time, a new index will be created. That one will go up through the chain. That's what we have seen in here as an example, right? So I had this sort of index, But if I keep inserting data, right, so these index get changed, all of the index that we have. So that's how that index will be changed from here. Hopefully making sense. Last part is composite search key, just to clarify one confusion that sometimes occur. So when we have composite search key, composite simply means we know that that can contain multiple attributes, like composite primary key we have, right? So in a composite primary key simply means there could be multiple attributes, right? So let's say I have created an index based on age salary. What does that mean? First, logically sort on age, and then if the ages are same, then sort on salary. That's what an index based on age salary means. Okay, so if this is my actual data, heap means unordered. If I'm creating an index based on age and salary, think about everything is logically sorted based on age. So that's what we can see. When the ages are same, at that time salaries are, these are sorted based on salary. Right? Same thing if I am creating an index based on salary and age, now we can see the output is different. These two are not equal, right? So this one is saying first sort everything based on age, and if the age is same, salary is same, sorry. First sort everything based on salary. If salary is same, at that time sort them using age. So that's what we can see. So everything is sorted based on salary. When the salary is same, at that time this one is sorted based on age. So definitely these two are not equal. Okay, remember that thing. So if I have an index based on age and salary, but I am writing a query on salary and age, these two are not equal. Okay, just to clarify further, so let's assume I have an index based on age and salary. So this is what the logical structure is currently, and I have a query like this. Can we use this index to look up search condition age equal to 20? So if in the query I have a condition age equal to 22, does this index help? Yes. Why? Because everything is stored in the order of age. So since age equal to 22, that is what we are looking for. So we can use this logically sorted data to create the index and figure out everything from there, right? What about this condition there? If age is greater than 22, does this help? What do you think? Yes, no? Can you use this index to answer this query where the where condition is age greater than or equal to 22? Yes, definitely, right? Because everything is sorted based on age. Excellent. What about this one? Can I use this index to answer this query where salary is equal to 2000? No, right? Yep. So now you understand why not. Since the condition is only saying salary equal to 2000, but the data is not sorted based on salary. So no. Salary greater than or equal to 2000? No as well. What about this one? Is 22 and salary equal to 2000? Can I use this index? Yes or no for this query? This one condition is age 22 and salary equal to 1000. Yes, we can use this one, right? So first we'll figure out whether age is equal to 22. If age is equal to 22, then based on there everything is sorted, we know, right? So there we can use this salary condition as well. What about greater than? Definitely yes, right? That's what we can understand. Hopefully these things are making sense that we have talked about. So that's all for today. Next we will talk about query processing. Hopefully these things are making some sense. Feel free to ask any question. If you have tried that web page that I have shared, you can try many other data structure there, linear search, binary search, B+tree, everything you can practice in there to see some examples. After that, if you have any question, feel free to ask next week as well. So that's it for today. Thank you, everyone. See you next week. Someone is asking for page number 36. This is page number 36. So this one is for HIF file on average, right? So that is the best case for linear search that we had. So this one is 70,176 because of n by 2, the average that we had for HIF file. So this sort of calculation might be there in your exam. Okay, so whatever we have learned today. Okay, thank you, everyone. Take a few minutes of break, then join your tutorial if you have one today. I'm here for another 10 minutes. Feel free to ask any question if you have. Index means logically sorted or just B tree. Index means logically sorted data, and we create that using B plus tree. Where is that thing written? Somewhere it was written. Yep. So these are different types of index that we are creating. Okay, so today we'll only talk about B plus tree. We also have hash index there. So these are different type of indexes that are available. Not pretty clear about the overhead, why it is that much for expectation. Yep. So that one should be very easy. Let me just figure out. Yep. So look at the question and what this information is giving us in here. So this one is saying that you have 2 million record, right? So here it's saying you have 2 million record, and each record is 200 byte long. So that should be the easy calculation. So to store this record, how many space do I need? This number of record multiplied by 200 record, because each record is 200 byte long. So this one multiplied by this one, that one is the expectation, right? But now we can see that because of the header data, because of some wastage, we have much more than that. Does that make sense? Yep. Someone is asking in this page as an example. So every time we are comparing the target key to the first key in the index space and rounding down and rotating down. Yes, that's what we are doing. So we'll always from the root, start from the root, and then figure out we want to reach the leaf node, right? So which side we need to go. Think about like binary search sort of thing. So if we're looking for, let's say 8, So we'll compare with 17. So since 8 is less than 17, that's where we need to go, right? So in here, we can compare with 5 or 14, that's fine. So let's say I'm comparing with 14. So 8 is less than 14. So it will be on the left-hand side of 14, so where left-hand side is pointing, right? Or if you're comparing with 5, that's fine. So 8 is greater than 5. So you can go to the right-hand side of 5. So both of them will point to the same location. So in this node, we have 5, 7, and 8. Here we compare whether 8 is there or not. Since 8 is there, then we return that yes, 8 is here, right? So that is the thing we do. So we always start from the root and we go down the path that we have. So like in here. Okay, so that means we can compare with any key within a page. Yes, yes, that's what you can do. Right. So you need to figure out with which you need to compare. So let's say I have a 20 in here as well. Okay, and you are looking for 25. So at that time, greater than 5 will not help, right? So greater than 5, if you simply go to in here, that will not help. So greater than 5, but 25 is not less than 14. So you need to go to this pointer, not this pointer, then this one. So wherever the right hand side of 20 is pointing, only there you will go, right? Yeah. Good question. Only leaves are actual data, others are indexed. Yes. So these are the actual data. That's why it doesn't stop at 30 in the root, right? So if I am looking for 30, this is the index that I have. It keeps going, right? Only when it reaches this node, and at that time it will say that yes, 30 is found. Now we can see that 30 is found. So all of these are actually indexed, saying the data is on my right hand side, but here is the actual data that we have. Looks like no other question. Okay, so that's it for today. Thank you, everyone. See you next week.